Hi students, welcome to Lecture 8, Walls, Steps, and Reps. So these three are major types of grade change devices. In an outdoor environment, when you have significant elevation changes that are too difficult or unsafe to be accommodated with slopes, these grade change devices will come into play. We'll break this lecture down into multiple parts. In the first part, we'll introduce retaining walls. So, what is a retaining wall? It is a grade change device that allows the greatest vertical change in the shortest horizontal distance. It retains volume of earth behind it, and it can be multifunctional and should be multifunctional whenever possible. This picture here shows a wall on campus that also provides a sitting space. I want to use another illustration to explain why we need retaining walls. So suppose there's a need to turn the sloped area into a flat tennis course, for example, so that you and your friends can play tennis here. And this area indicated by the white line is the only space we have. Now, if we simply remove all the soil in this area, that will lead to, yes, a slope that is too steep with all kinds of problems, right? Erosion, collapse, you name it. So instead, we only remove part of the soil and we'll need to use a wall to retain the soil behind it, like this. Now, of course, this is only one of the scenarios where a retaining wall is needed to avoid steep and unusable slopes. But hopefully that helps you better understand the purposes of a retaining wall. Now, before we get into the guidelines of grading retaining walls, you need to remember that this is design. Okay? Changes in grade often present wonderful design opportunities. And the design of a retaining wall needs to consider the functions of the wall, the experience that this wall provides, and the visual quality the wall creates. Next, we'll go through 6 key guidelines for retaining wall design. So there are 4 basic ways to use retaining walls. The first 2 are 2 ways of using a straight wall. The key thing to notice here is that, shown below here, the bunching of contours at the end of the straight wall is not correct, simply because you should not use the short distance of the width of the wall at the end here to take up 1 foot of elevation difference. So the first type of straight wall takes up the slope on the uphill side of the wall. That means that all the elevation transition happens on the uphill side, whereas on the downhill side, elevation are almost the same. Okay? And in this scenario, the design must direct water away from the wall, so the contours have to form a small swell when connecting to the wall here. The other type of straight wall is exactly the opposite. It takes up the slope on the downhill side of the wall, meaning that all the elevation transition happens on the downhill side of the wall, whereas on the uphill side, elevations are mostly the same. Okay? And drainage away from the wall here would not be much of an issue, as the blue arrows already shows drainage away from the wall. The other 2 types of basic retaining walls are angled walls. One type of angled wall has its angle pointing downhill, creating a flat space that is lower than the area on the other sides of the wall. Okay? For this type, drainage design should pay attention to two areas. The first area here, again, you need a small swale to direct water away from the wall. The second area is that the slope needs to pitch in a way to drain that corner, this corner, outward. Okay? The second type of angled wall has its angle pointing uphill, creating a flat space that is higher than the surrounding area. Similarly, for this type, a small swale is necessary to direct water away from the wall in this area, and the slope needs to pitch in a way to drain the corner outward. Okay? Now the second guideline is that the top of the wall is nearly always level or flat, or the wall height can step to relate to the adjacent slope, as the bottom figure shows. If the wall doesn't step, it may soon get too high, as the white arrow shows here, requiring a different construction technology. When it gets too high, it needs to be strongly built, right? It may appear too heavy. It may cause undesirable closure of the space. It can't function as a sitting wall anymore. So those are all kinds of different reasons to step your wall. Now, occasionally you may indeed see a slanted or sloped top for the wall, but it is not the way we would recommend. Because a sloped top is really challenging to build, especially with concrete. Okay? The aesthetics isn't great either, and you can see here that the sloped brick retaining wall appears to be working against the brick building behind it. Now, the third guideline is an important one. The wall's design must consider the quantity of the earth to be retained and its drainage. Notice that improper drainage causing water seepage into the backfill of the wall is the number one leading cause of retaining wall problems. So first of all, you need a swale or other drainage control, such as a drainage inlet at the top here, to divert water away from the wall. Second, if the wall is not dry laid, meaning that mortar is used as the binding material for the wall, then ways to reduce water buildup behind the wall are needed at different locations on the wall. Weep holes, as shown here, that are regularly spaced close to the bottom of the wall are commonly used. So if the wall is quite high, the number of weep holes will need to increase, not just only close to the bottom anymore. It might need to be more evenly distributed in the vertical direction, even in a grid pattern. Okay? Lastly, don't forget that the wall's footing extends into the soil, so a pipe above the footing that collects all water draining towards the foundation is often necessary, as shown here. Okay? Now, the fourth guideline, if the wall is over 4 feet tall, the LAs, us, will need a structural engineer to verify the design is stable enough. And this is the reason why in this class, we ask you to step to the top of the wall and maintain a maximum height of 4 foot. Okay? Next, if walls are used to protect existing trees, they should be at or beyond the tree's strip line, meaning that you should not build a wall too close to the tree within the drip line. However, in reality, designs that truly allow enough space around the trees are not very common, such as the one shown in the bottom left picture here. That's a much better design. More often, you'll see pictures such as the two on the right. Okay, these trees may be able to survive, but they would have been much happier if more soils were retained around its roots when the walls were built. Okay? Now, the sixth important guideline is that function and material choices are always very important design considerations. For instance, if the wall is also intended to serve as a sitting wall, how wide should it be? Should the height vary to accommodate different length of people's legs? How does the surface feel during a hot sunny day? Right? The context of the wall is also important. Is the wall in a formal or informal setting? For example, if this is a wall for a normal residential patio, an informal appearance with natural materials may be more appropriate to provide a more intimate atmosphere, right? Keeping the user characteristics in mind is also important. In this example of a sensory garden in a senior care facility, the height of the wall needs to allow seniors in a wheelchair to access the plants above the wall. The stone material here also offers a rich texture, details that are very important to provide interest for people with limited mobility. Here is another example of a functional wall used to screen the view to the parking lot behind it. So the wall needs to be tall enough to hide the parking lot, but how can we make the tall, heavy wall more visually interesting? You can see from the above picture here that the color, the materials, and the geometry of the wall are coordinated with the design of the porch columns in the background. So those are the 6 key guidelines for retaining wall design. One other design consideration that I want to mention here is skateboarders. Okay, a major threat to retaining wall in public spaces. Short walls below 2 feet are their favorites. So think about how can we prevent the skateboarders from ruining the top of the walls with design strategies instead of using the metal skate guards in the bottom left picture here. How can we integrate, for instance, an uneven top space with a rough ground plane to achieve the goal without being too obviously against the skateboarders, right? And those are not just considerations for short vertical retaining walls. In this example of the renowned Olympic Sculpture Park in Seattle, the designers probably also overlooked this issue when they designed the concrete tilted walls. Seems to be a really fun feature for skateboarders here. Okay. Next, let's talk about how walls should be represented in a construction drawing with contours and spots. In terms of contours for straight walls, you can see from the plan that the contours stop once they hit the wall, right? Where did they go? From the 3D view on the right, you can see that they continued along the wall or around and then along the wall. Now, we don't really draw those segments of the contours running along the wall on the plan because they would make the drawing cluttered and confusing. However, an important skill that we develop through this course is the ability to visualize where the contours go along the wall, even though they don't physically show on the drawing. Okay? Similarly, for the angled walls, the contours on the plan stop when they hit the wall. It's important to recognize that they connect around the wall because eventually you need to know how contours connect in the surrounding landscape off the wall. So knowing the connection points here will be really important. Okay? Spot elevations are really important for the contractors to build the wall correctly. Again, even more important than the contours. And specifically here, we should use top of the wall TW and bottom of the wall BW to label the spots. Now, this is likely the most important slide of this lecture. Students in the past have made numerous mistakes marking the locations of the spots for walls. So please pay attention here. And this is slide number 28. Okay? For the top of the wall, TW, you will need at least one TW for each wall segment if the top of the wall is flat. So in this example, you need at least two, 1 and 2, because there are two wall segments. Now what we see here are 3 TW spots at 3 locations, including the corner and the ends. That's what you should do in this class to make the wall design crystal clear, even though all the TW spots are at the same elevation here because the top is flat. Now, if you have a stepped wall with multiple segments, and each segment has a different TW elevation, then every segment needs at least one TW. And TW should be marked on the wall in the plan view. On the wall. Okay? See where these TW spots are marked. And for the bottom of the wall, BW, they should be marked at all corners and sides. So if you look at this example closely, the L-shaped wall here created a space that is higher than the surrounding area. And in this area, here, the elevation transition is just starting. So there's no elevation difference between this spot and the other spot on the other side of the wall. Okay, and that is why at the end of this wall here, you only need one BW. However, when we get to these two corners, as mentioned before, the higher space led to higher BW elevations at these two locations. In other words, the purple spots are higher than the pink spots, so they all need separate BW labels. So, as a general rule, 3 spots are typically needed at corners and 2 are needed at the end of the wall. Okay, and the key is to distinguish where there is a difference in elevation between the two sides of the wall. Now let's look at a few examples. Pause a few seconds here and think about why we need at least 4 spots here for this wall. 1 TW because the top is flat. Okay, multiple BWs here where material changed between concrete and bricks. And there's also a slope change noted by this BW on the far right. So it's basically following the principle that we taught you before, right? Anywhere with a material, slope, or geometry change, a DW is needed. Now, note that there should be other BWs on the planter that is higher than the steps. They are just not shown in this view. Okay? Now, here's an example of a stepped wall. As mentioned before, in this scenario, every step needs a TW spot marked where the stepping occurs. Okay? In terms of the bottom of the wall spots, this example shows two BW spots at the beginning of the slope on the ramp here, and then at the end of the wall there. Okay? Okay, that was how we represent retaining walls with contours and spots. With this slide, we introduce a new concept, building walls as retaining walls. So before this lecture, we talked about wood-framed building. You were taught that we need to maintain a certain elevation difference between the building FFE and its corners. The corners should be 6 to 18 inches lower than the FFE, right? But buildings with stronger materials do not necessarily have to follow that rule. Those made of masonry walls or concrete can retain soil on their own. Sometimes they are called foundation walls. Okay? For those of you unfamiliar with the term of masonry, it refers to the building of structures from individual units, which are often laid in and bound together by mortar. So think of brick buildings and those made of concrete blocks. Okay? So those building walls are able to retain soil on their own, which means that the exterior elevation here can be higher than the building FFE as shown on both of these drawings here. Exterior higher than FFE, exterior higher than FFE. Okay? In terms of contours for these building walls, they behave the same as the straight and angled walls from previous slides. And in terms of spots, they should still be expressed as corner spots instead of being labeled as BW. Okay? Lastly, here is another illustration showing the contours on a real building. So this concludes the first part of Lecture 8, Retaining Walls. We will continue to discuss steps and ramps in the next video. Thank you very much.